Okay. There we go. All right. Today we're going to talk about some power issues and confidence intervals for effect sizes. You don't know it how sort of wonderfully lucky you are as a group. SPSS is now calculating confidence bounds for effect sizes for you, which we used to always have to take this and do this by hand. So this simplifies things for you a great deal because we don't have to do this by hand for the most part. However, there are some issues that go into calculation of confidence bounds for effect sizes. I want you to be aware of so you kind of know what's going on and sort of how this starts to impact interpretation of some of these, and then talk about some power issues here. Okay, so just as a recap, so we talked about experimental errors, right? And the two types of experimental errors that we can have. We can have type 1 errors. This is when we reject the null hypothesis, when the null hypothesis is in fact true. Here we've claimed that we found something when there really is nothing to be found. We call this a type 1 error. Our type 2 error, this is the type of error where we fail to reject the null hypothesis. We're not saying that there is no effect. We just say that we don't have enough evidence to claim an effect, when there actually is a relation or a difference out there that we could claim or that to be found, right? When we're doing our analyses, we're primarily concerned with controlling our type 1 error. What do we go through? What do we set that controls? How do we set our type 1 error, Johnny? Alpha determines our type 1 error, right? That tells us our tolerance for making a type 1 error within our system, okay? We're typically less concerned with opportunities to make a type 2 error. Okay. Thoughts on why this is what we do, and we make way more type 2 errors than type 1 errors. But why might it be problematic for not identifying or sort of making too many type 2 errors?
So if I'm making a type 1 error, I'm saying something exists when it actually doesn't. While the type 2, I'm saying something, it's a false positive. And I could almost see like us prefer to make a false positive to say like, hey, something does exist rather than.
The type 2 would be a false negative, right?
Yes.
Okay, and so yeah, Jalen, you want to expand on that?
Aren't we like currently having an issue with this where like we weren't wanting to publish null findings? So like we could be looking at something really cool and there could be an effect, but if it's not powered enough, we could get a type 2 error and then no one's ever going to be able to like replicate that and add more power to actually find an effect.
Yeah. So this is really what starts to play into some of this stuff, right? Like in science, we're always worried that someone's gonna get something for free. I'm like overly concerned that someone's gonna get something that they don't deserve, right? That I'm worried that someone's like, hey, you're gonna get to claim an effect when you shouldn't claim an effect, and sort of fine, right? We want to make sure that the things that we're claiming that we have evidence for, right? But the whole system is set up around type 1 errors. Type 2 errors, though, are problematic in terms of advancing science because oftentimes we don't have evidence for an effect. That doesn't mean the effect isn't there. Now, what we do is we interpret, whether we want to realize it or not, as failing to reject the null as evidence of nothing going on. There's nothing to see here, when in fact, that's not the way we should, like, null effect doesn't mean that there's not anything there. It just means we don't have evidence to say that there is, but that's interpreted as a zero effect. And so then what ends up happening is, let's say Allison finds something and then I don't, and then I say, well, is the unclear, right, whether or not this is a thing, and then I'm questioning Allison's work and things along those lines, or Allison goes and tries to find something, she doesn't find an effect, or like, well, I guess there's nothing to see here, and I move forward. But what we're doing is we're not considering the impact of power and whether or not our design was set up to maximize our opportunity to find something if it might have been there, which leads to publication biases, which leads to replication crises. I threw an extra syllabi in there. But this is sort of part of the reason that it's something that's held us back quite a bit. in terms of our concern with type 1 error, this is just how our test is set up, right? It's all set up to be targeting type 1 errors. We also have difficulties calculating type 2 error. There's some mathematical complexities that make this harder to do. And so because it's harder and not accessible, then we are less likely to do it. Also, our awareness of type 2 errors will make us kind of sad if we focus too much on it, right? In social sciences, behavioral sciences, what's the size of effect that we're typically looking for? No. What do you think, Mesa? Just in terms of size of effects, like what would you guess the size of effects we're generally trying to chase down in social sciences?
Like a probability or like a how much
Like
longer?
sort of the magnitude of effects. Are we looking at small effects? Are we generally dealing with large effects?
Small effect.
Pretty small effects, right? Issue is a lot of stuff. We've got these really elaborate psych theories about behavior and psychology, and so how everything fits together, and nuanced assumptions about how this is going to influence this. But we're also talking about human behavior, and so our measures are garbage, like they're all over the place, like filled with error. There's about 1 billion different influences on behaviors and things along those lines. And so what ends up happening is the effects that we are looking for are generally really small. In order to adequately power designs where we have small effects, how many people do we need? Way more than we almost always ever have, right? Which sort of makes this feel a little bit almost like a fool's errand, right? Matt, you're from Las Vegas, right? If I walk up to a table and I say, hey, Matt, come play this game. So house's odds are about 80%, right? So 8 times out of 10, house is going to win. Other 20%, you get a marginal payout. Like, are you going to play that game? No. Nope, but we do it all the time. This is what we're always doing with our underpowered studies. Okay. It's not saying that we can't find anything. It's just saying we're probably not going to find anything. And then if we do find anything, sample effect estimate that we're going to get is probably much larger than the actual population effect, which then contributes to a whole bunch of stuff, right? And so this is an unfortunate thing to think about. And so I would rather just do my study and see what happens as opposed to think about power. And so all of this stuff makes this type 2 and power, this type 2 error stuff kind of anxiety provoking for us. All right. So we're talking about power. Yes.
Sorry, I didn't mean to like.
No. I was on a roll with it, you know, so.
Okay, so with type 2 error, we make the mistake of saying that there isn't an effect in a study when there is one.
Yeah.
And then type 1, we say that there's an effect when there isn't because we are underpowered.
Type 2 errors, this is where we're underpowered. Type 1 error is we just kind of make a mistake, or we have a bad method or bad methods or sort of measurements or things along those lines, or a funky sample or something along those lines.
But, okay, so type 1 is just when we make a mistake.
When we claim that something's there when it's actually not.
Would it be like saying that an effect is there? Or, okay.
Yeah.
Thank you.
Got it? No, don't apologize, you're good. All right. There we go. Okay, back to power. Power, thinking about power as very literally long-term predictive probability of rejecting the null given a particular effect size, alpha level, and sample size. Okay. Power is saying if I were to replicate this study over and over and over and over and over again, what proportion of those studies would reject the null hypothesis if the null hypothesis is false, right? So generally when we're looking at using at these power analyses, what we want to do is look at the expected power of a planned study prior to data collection. Okay, so here's the effect I think I'm looking for. Here's the sample I have. Here's what I'm going to do. What's the probability of me finding an effect if there is one to find, right? Or alternatively, again, prior to collecting data, me going through and saying, here's the effect I'm looking for. Here's what I'm going to do. Here's the power that I want. how many people do I need to achieve that level of power? Okay, used appropriately, power calculations all happen before I even go through and collect the data. This is part of the design process of a study, okay? Other thing to remember is our power analysis is not an exact science, okay? We can think about power being an effort and endeavor to try and see, is my power closer to 0.8 or 0.3, right? Any thoughts about why these power calculations are far from precise and are very much a guesstimate? Yeah,
Because you don't know how big your effect will end
Yeah.
up being.
a lot of times, right? If you're doing something that no one's ever looked at before, this effect size is the big thing that goes in. I need to know what effect size I'm chasing down. And if no one has ever done anything ever remotely close to this before, it starts to become very hard to determine sort of what I'm chasing, what I'm chasing down, right? We also have issues with measurement and design and things along those lines. So even if Kate has found something, and so I want to say, okay, she found this with this analysis and this model with these variables, and I'm going to do something completely different. Hard to know. Like I might get a general ballpark idea for the likely magnitude of that effect, but with a different design and a different analysis, that changes everything a little bit. And so I start to become less confident in sort of what I'm actually looking for. Yeah.
I was just gonna ask if like 80 and 30 were arbitrary numbers. you
Yeah,
put
just
up? Okay.
arbitrary. This, it's just like it's a little or is a lot, right? And this is really a horseshoes game, right? Like, so I can go through and often for grant proposals and things like that, you say, okay, here is my power calculations. But no one should ever take those unless under very specific circumstances where we have very, very good estimates of the effect size and other studies that have looked at this with using similar designs and methods. It's not something I would want to put a whole lot of money on, okay, in terms of that. All right. Other thing that we're thinking about here is this idea of adequately powered, right? Within behavioral psychological behavioral sciences, we talk about power at 0.80 or 0.80 as being our acceptable standard. So this says very literally that over repeated replications, 80% of my studies or 80% of my replications will identify this effect if it's there to be identified at sort of whatever level I expect it to be at. Okay. Now, if we have less than 80%, we would say that that's an unacceptable level of type 2 error, right? Honestly, power sort of most like I think for psychological science, most of our studies are powered about 0.5, right? Somewhere in that, right? Like where it's basically a coin flip, irrespective of whether or not there's something out there to be found. I'm at about 0.5 on whether or not I detect anything or not, right? I don't know. I sort of got that somewhere. I can't remember exactly, but that seems like a pretty sad situation, right? If it's basically a coin flip or random occurrence on whether or not I find the thing out there or not, right? On the other hand, if I have power over 80, well, why not have power at 1, right? Like, why not just like always have enough people to, or a large enough sample to be able to identify the effect that I'm looking for? Well, inefficient use of resources, right? If I'm running a repeated measures design and I need 30 people because I'm looking for a big effect and I only need like 30 people to actually get the thing that I'm looking for, and I go ahead and run 150 just because I want to make sure, I'm going to have ultra precise estimates for University of Wyoming students, right? So it's probably not a good utilization of resources. There's also the potential for unwarranted conclusions, right? If I have a sample of 100,000, any correlation between anything that I look at is going to be statistically significant, and I might start making a big deal about that. But if I actually look at the correlation coefficient, it's 0.02, right? And so if I go, I have significant effect of this and that, like, well, statistically significant, and as in my data is saying that, yeah, the association is not exactly 0, but it's not something that's sort of meaningful or has any sort of practical utility. Yeah, Kate.
Is there a acceptable range around this arbitrary 0.8 that is, I mean, because we're talking about being too low or being too high. Like you just have to hit 80 or point
Right,
eight.
I don't know, what's your level of for risk tolerance and sensation seeking, right? This is essentially what it is, like if I'm putting together my study, like how comfortable am I with the possibility that I just don't have enough people to test the thing that I wanna test,
Mhm.
right? So here's the thing, and this is an issue, now if I'm getting money from the government to conduct something, to test some hypotheses, they're probably gonna wanna see at least that I've got reason, like what we would normally say sort of reasonable power here. If it's your thesis, right, and I'm on your committee, like I'm not terribly, because like if adequate power was the entry for doing any research that we would have a fraction of, we would do a fraction of the studies that we actually do, right? But if I'm sort of fine recognizing that I'm underpowered, and I understand that going in and recognize the potential impacts that could have on my thing, then, right, it's not reasonable to ask students to have 500 people in all regression analyses that they ever run in the universe, right? So I'm more interested in you understanding kind of what's going on now. So it kind of depends on the context, right? So you would go through, and this is what often happens, right? Like, so you'll go through for your thesis and you're hopefully run a power analysis and say, based on the best that we can do, like I would need to have a sample of 120 in order to achieve adequate power. And then you go through, and so we say, okay, and then you go through and you do something, and so you collect your data, and you get 90 people, right? Well, it's not 120. I'm not. No one hopefully is going to kick you back. No, like this wasn't the agreement, right? But like sort of recognizing sort of what impact that has on the likelihood of you detecting effects. And so just thinking carefully through this stuff. Questions about power and what we're talking about here. Okay, let's talk and think about this in terms of an empirical demonstration. This will be helpful. So Aronson at one point was studying something we call a stereotype threat. Do people familiar with stereotype threat? Okay, so basically, so the idea is that sort of acknowledgement and recognition of stereotypes can have an actual impact on performance. And so in this study, what they did is they had white men come in to take a math test, right? And they had two conditions. In one condition, they just let the guys come in and take the math test, right? In the second condition, what they did is they came in back, okay, here's a math test. P.S. Asian American students tend to do better on this than white students do, but here you go ahead and have at it, right? And so in one case, we've got a control group just taking it under without any sort of influence. In the threat group, what we've done is we've not threatened anybody, but we've sort of gave them information that's consistent with the stereotype, and we want to see how this impacts performance. And so what we did is we go through and they run this with 20 people in each group, and then you get mean performance in the control group, mean performance in the threat group, and relative standard deviations here, okay? So if we wanted to go through and test the power of this and sort of talk about like what we're looking at, what are we talking about in terms of this within a power context? What we would do is we would select 20 observations at random from a population of scores with a mean of 9.64 and a standard deviation of 13 or 3.17. Okay, and then we're going to take another a random 20 observations from a population of scores with a mean of 6.58 and a standard deviation of 3.03. Okay, so within Abby, and this is, so if I randomly select scores from a distribution with a mean and a standard deviation here, are my 20 scores going to have that mean and standard deviation?
I'm confused on what you're asking.
Okay, so if I have a distribution and I know that the mean is 9.64 and the standard deviation is 3.17, okay? And I go through and I just randomly select 20 scores from that.
Mhm.
So I get a sample. of 20 from this population, is my sample mean gonna equal 9.64?
Oh, I see what you mean. No,
No.
not necessarily.
Is my standard deviation gonna equal this?
No.
No, right? So if my N is equal to 20, right? Any individual sample is not gonna be equal to those parameters, right? I'm gonna have some sampling error, they're gonna be around. But if I do this and I were to collect all samples from size 20 from this distribution, and look at the mean there, what would the mean be? If I took the sampling distribution of size 20 from this, then what would the mean of my sampling
It would
distribution
be
be?
equal to mu.
It would be equal to the population mean, okay? So same thing, what I'm doing is we're saying that if we say for white men taking this test, the mean score is this, here's the standard deviation. And for white men taking this test under the threat condition, the mean score is this and the standard deviation is this, right? If those are true population parameters. If I were to go through, and we're thinking about power procedure, what I would do is assume that these are population parameters. If I were to take a sample of 20 observations from this distribution, right? And log those, take a random sample of 20 observations from distribution without those characteristics, do that. And then what I do is from each one of those samples, I go through and calculate and record a t statistic for the difference in means, right? So I just run my independent sample t-test, okay? So I go through and 20 scores from this distribution, and then I've got right? So I take 20 scores from this distribution, 20 scores from this distribution, go through and calculate my mean difference, calculate my t, okay? And then what I do that is I do that again 10,000 times, okay? What I'm gonna get, if I go through and I plot the frequency of the distribution of those t statistics, okay? These are t statistics for 10,000 replications, 10,000 samples drawn from each one of these. If I go through and I redo that 10,000 different times, and then I plot the distribution of my t statistic, what I'm gonna get is I'm gonna get a distribution of t scores, right? Now, in this case, my critical t value with 38 degrees of freedom, because I got 20 and 20 minus 2, 38. My critical t here is 2.042 or 2.024, okay? And what I would find in this situation is the mean of my t's is 3.12, right? But if I go through and I look at in this distribution, and I take a look at what percentage of my t scores are exceeding this critical value of 2.042. Well, I got about 0.86 of those that are going through and exceeding, okay? This here is going to tell me what my power is, okay? So the idea being that for any one of these samples that if these really are the population parameters for the control group and for the threat group, right? The question is, with sample size 20, how often am I going to reject the null hypotheses given that there is a difference, right? Well, this would say, if I go through and do this, it would say about 86% of those, right? And so if that's, and then so the remainder is not. So these are still coming from two populations that are different. There is a difference there. But about 15%, 14% of those samples are going to fail to reject the null just because of random sort of stuff, right? So in this case, Allison, in this example, what is my power here?
0.86.
0.86, okay? That's going to give me my power. So essentially what we're saying, remember we talked about power as being sort of over repeated replication, the proportion of tests that are expected to reject the null hypotheses when the null hypothesis is false. So even though these are very different means, right? And there is a difference between folks completing this exam under the stereotype threat and those completing it not under stereotype threat. With sample size 20, not all of those tests are going to reject the null hypotheses. most of them are about 86%. And so we would say that we've actually got pretty good power given the effect in this study, but it's not perfect because sometimes we're gonna miss. And
This is a dumb question,
I'm sure
but
it's not.
is the 10,000 times like sarcasm or is it for serious?
It is just sort of saying a lot and a lot
Okay.
and a lot, right? So I mean, technically, if we were to do this sort of for all possible samples that could be drawn from each one of those, that's technically what we're looking at here. It's just saying, if we did it 100 or sort of lots and lots and lots of times, yeah.
0.8559 was calculated using the t-value.
No, this is just like, if we were to go through in this hypothetical and just plot out all of our T statistics that we would get. And this is kind of where we would.
Okay, so we wouldn't have needed to calculate that.
No,
at
no,
least
no,
at this
no,
point.
no.
Okay.
I mean, technically, that's coming, we'll talk about where we get that calculation from
Okay.
with our power stuff. Okay, so people kind of see conceptually what's happening, sort of how we're sort of thinking about power from a replication standpoint. Okay, another way we can think about power is think about power as a function of overlapping distributions, okay? If we take a look at, and in this case, we'll just use a one sample test, okay? And in this diagram, if we think about distribution of the sample mean when the null hypothesis is true versus the distribution of the sampling mean when the null hypothesis is false, okay? So in this first example, so the null hypothesis here is that there's a population mean of 80, right? And so if there's a population mean of 80, we have a distribution of scores that sort of go from here to here, right? So this is kind of this null curve here. But if we go through and we take a look at the sampling distribution of the mean when the null hypothesis is false, right? Here, let's say under the null hypothesis, our population mean is 80. Under the alternative, the actual population mean is 86. Okay. If I go through and I plot out the sampling distribution of means for the null, and then I go through and I actually calculate the sampling distribution for the alternative where it's sort of overlapping but not distinct, right? What we see is that because these are overlapping distributions, if I were to go through on the alternate curve, because that's reality, that's actually what's going on in the population, right? And if I were to take a sample from that distribution, right? Where are the bulk of those samples going to come from?
Looks like the alternative.
What's that?
It looks like the alternative.
Yeah, if I'm going through and I'm taking a look, right? So if this is the alternative hypothesis, okay, so let's say here's our curve under the null, right? And let's say, because we want to say that if we find a mean that falls within the tail of that distribution, that's when we're going to reject. Okay, so here on our null curve, we go through and we calculate this alpha level, this dark shaded area right here, right? So if I find a mean that falls in that alpha level, that's when I'm going to go through and I'm going to say that I reject the null hypothesis, right? How about this? Let's do this. I go through and I say, here's my sampling distribution of my null, okay? So this is a mean of 86, and I say, all right, here's alpha 0.05, okay? So if I were to sample anything from this distribution, if I get something in this tail, that's when I'm going to say, then I'm going to reject the null hypothesis, right? People with me on this? Okay. So if the actual population mean is not 86, if the actual population mean is 80, as specified under the null, how often am I going to get stuck in this tail? Only 5% of the time, okay? But let's say in actual fact, my population mean isn't 86. the mean of my population, or isn't 80. Mean of my population is actually 86, okay? Is this the distribution we're working with then, under the alternative? No, we've got a different distribution, right? And that different distribution maybe looks something like this, right? And here the mean value is 86 and not 80, okay? Now, if I go through and I start sampling from this population with a mean of 86, is my sampling mean always going to be 86? No. Sometimes it's going to be more than 86, sometimes it's going to be less than 86. But where the bulk of samples out of that distribution going to fall? Yeah, so all of this, and if I go through and I take this score, whatever this score is for alpha 0.05, and I run this up. And if I pull a sample from my alternative distribution, which is what's actually going on in the world, what happens if I get a sample that falls right here? Am I going to reject under the null? Nope, I'm not. What if I get something right at the mean? Am I going to reject under the null? What if I get something even a little bit to the right? Am I going to reject under the null? Nope, it's only when I get sort of in this tail. So everything going on in here, even though these are all values under my alternative hypothesis, these are all values of the null under my alternative distribution that I'm still going to fail to reject the null. And so these, what do these represent in terms of my errors?
You wanna know which type of errors?
Yeah, what type of error?
Type 2.
Why is it type 2? What have I done here?
Rejecting something that is actually.
So again, all of this is occurring in sort of the actual population value, right? But it's overlapping with my null distribution. And if this is my cutoff for claiming a null, rejecting the null under my null, but the values that I'm getting are over here, what am I going to do?
You're gonna fail to reject, but
Yes.
it's still technically different.
Yes,
Yeah.
right. So even though there is a difference between these two, what I'm doing is I'm failing to reject the null hypothesis here, even though the null hypothesis is false. And so what type of error am I making here? A type 2 error, right? So now if I'm down on this end, now I'm past the alpha level and I'm sort of making the correct decision. I'm rejecting the null hypothesis, right? But what we're seeing here in this graph is this heavily shaded area. This is my critical region under the null hypothesis, right? So anything to the left of alpha, these are all my type 1 errors, right? Anything that's in this distribution from here over, I've made a type 1 error. These are all values of this sampling distribution that aren't going to exceed alpha under the null, that are still going to be categorized as type 2 errors. Everything from the right of this to the right of this unshaded distribution, these are all situations where I'm going to make the correct decision. This is equal to my power. Okay, so what proportion of this distribution exists in this area? That's telling me how much power I have. Okay, so Allison, I'm going to go back to you just real quick. In this example, right? In the previous example, my power was 0.86, and so I was pretty happy about that. In this example, am I excited about the power here? Why not?
It's not 0.8
Yeah.
or below.
What would you guess it is? Point 0.3, maybe 0.3, 0.4. But basically that's saying 30 to 40% of the time, I'm only gonna find this effect 30 to 40% of my replications, right? The majority of the time, I'm gonna fail to reject the null, even though the null hypothesis is false. Yeah, Johnny.
I just wanna make sure
Yeah.
I'm following.
Yeah.
So from that alpha kind of like line, if you will, to the left, that's gonna be a type 2 error.
Yep,
And then everything to the right of that, that's gonna be my power.
exactly.
Okay.
Exactly.
Oh.
Okay.
Can you repeat where the type 1 error?
Yeah.
What's up?
Can you repeat where the type 1 error is?
Type one error isn't in here.
It's not, okay.
It's not, type 1 error isn't involved in
Thought you
this.
said something about type 1.
No. Well, the only place type 1 error comes in is in the selection of our alpha, right? But that is only relevant if the null hypotheses were true. If the null hypotheses were true, then we're saying that only past this point would we. So we're saying that anything past this point would suggest that the null hypothesis is not true. But we're gonna just, there's 5% of the time, we're gonna make that sort of error, and we're saying, okay, that's our type 1 error. But in this scenario, we can't have a type 1 error because my alternative hypothesis is true. And so anything that happens to the right of that, that's my power. Anything to the left, that starts to go through and be my type 2 error. Okay, hold on real quick. What happens though if we start to separate this out, right? What happens if our distributions are no longer overlapping? If we keep everything the same, right? But now my value under my null is 80, so this stays the same, but my alternative hypothesis now has a mean score of 90, okay? Now this goes through and there's less separation and less overlap, right? So if I go through and I take a look, same thing here, still have the critical value that's based on my null hypothesis. This is my alpha equal 0.05. But now what's happened to the number of type 2 errors that I'm making in this scenario? It's going down, right? Because I've got here, anything that on my null or on my alternative distribution that exceeds that critical value under the null, I get to claim evidence for an effect, right? And so now, because I've created that distance, created more separation, I have less overlap between these two. Now, all of a sudden, the bulk of my samples that I can pull out of my alternative are going to fall beyond that alpha value that I set under the null. And so these are going to be correct decisions. I've still got type 2 errors, right? This shaded part is my type 2 errors, but I have less of them than I did before, okay? So conceptually, what happened, what changed with this scenario versus this scenario in terms of thinking power? What changed here?
More power?
I have more power. Why do I have more power? Johnny?
There's less overlap.
There's less overlap, which suggests what?
The populations are more different.
Populations are more different, which says I have a bigger what? Say it. Effect size. I've got a bigger effect. There's a bigger effect here than there is here, right? So here, my distribution, they're different, but they're different by this much. Down here, my distributions are different, but they're different by a bigger amount, right? So what we've done is in this scenario, like sort of all things being equal here, we've got more power in this test because we've got a larger effect size that we're chasing down. Here, the effect size is subtle. My distribution, my population is different. It's different by a small amount, right? Down here, it's bigger by a different amount. So what I've done is I've functionally increased the power here, okay? Now, when we're talking about power, we can increase our power a number of different ways. If I just have my population value is going to be my population values, right? And so if I'm looking at the difference between students in the US and students in China, right, on some sort of outcome, right, that those values are what they are, right? But if I'm looking for something in like an experimental study, right, what I might start doing is I might start increasing the magnitude of my, or the power of my manipulation, right? If I've got a pretty subtle manipulation, I'm kind of working up here. But if I really crank up the juice, now all of a sudden I'm at this point, right? Or what can often happen, this isn't necessarily a good thing. If I start using extreme group designs, right, I want to look at the difference between see people who are high and low in extroversion on some outcome. if I just like sort of go through and I can sort of sample people, find whatever, but if I like, okay, here's people who are really low versus really high. What I've done is I've increased the magnitude of those differences. Now we get into problems with biases with that, but thinking about the types of things that start to sort of shift these apart. Okay. So all of this is to say we can think about power in a couple of different ways, both of which correct. We can think about power from a replication standpoint, right? Like if I were to go through and sample from these two different populations and just run this test over and over and over and over and over and over and over again, what proportion of those tests would reject the null hypothesis if the null hypothesis is true, right? So we can think about things from a replication standpoint. But we can also think about things from an overlapping distribution standpoint. This is helpful for a number of different reasons as we start to pull in other stuff, thinking about here's my assumed distribution under the null, right? And this is an assumed distribution. It may not be a real distribution, right? But just assuming that the null hypothesis is true, this is what things are going to look like. Here's my actual distribution. Is this what's actually going on in the world? And sort of thinking about power as the extent to which my actual distribution overlaps with my null distribution and thinking about how that translates into power. Yeah.
Just to clear up
Yeah.
the red and the green,
Uh-huh.
so the big lightly shaded part, that's beta,
Yeah.
and then the little dark part is 1 minus beta.
Not the little dark part, so all this white piece here.
The white
The,
piece,
the little
okay.
dark piece, that's the portion of the null distribution that contains your critical region. Okay, so everything to the right of this line,
Okay,
that's your power. Everything to the left of that line, those are your type 2 errors. Yeah, I mean,
I was just, you answered it just now, but I was gonna ask, that when we put like conceptualize power in this image, the alpha would be like part of the.
always part of the null distribution, right? Because that's the only thing we're testing with our analyses is the null distribution. That's the only thing that we're concerned of, right? With our actual statistical tests, H1 doesn't exist. Like, we're not even concerned about that. We're just saying, like, assuming that the null hypothesis is true, what's the likelihood of obtaining data this extreme or more extreme, right? But if we start talking about power, now all of a sudden we do have to think about that alternative distribution because the null is not true. Like, we're working, the null distribution, the thing that's the source of everything that we're looking at, isn't actually play out. It's this. So what does that look like, and to what extent are these overlapping? Questions about this? Yeah.
Yeah, I thought I was clear, but I just got a little confused. So the bigger your power,
Mhm,
like the white shaded part, and especially in the second part,
mhm.
so the gray part is like our type 2 error is reduced, but we're not looking at the dark shaded
Yeah,
part.
no, that's just the tail of that null distribution that contain your critical value.
Okay.
So any score that falls from here over,
Okay.
that's when we get to claim victory and claim an effect.
Same with the one above.
Yeah,
like
same
the
thing here.
20A.
Anything that sort of falls in this or beyond, we get to
We're
claim an
good.
effect.
Okay, so that's why, okay.
Now, so what about what's happening down here?
Type, did you say type 1
Well,
or more type 2 error?
it's more type 2 error, but can I actually have a value that falls down there? No, down here.
Yeah.
No, because there's
Yeah.
that population doesn't even go down now. So that's part of the null distribution that has no overlap. And so these scores don't actually, those are non-existent values. Yeah.
So I'm just trying to like make connections with some different things, so. Because we can also like we have like guidelines with overlapping confidence intervals and how they relate to like p-value levels, if you will.
Don't
Can you connect that with power?
make it and throw it away.
Okay.
Different overlapping thing. So
Okay.
don't, yeah, I see what you're trying to do. That you're gonna confuse yourself. Don't worry about that. This is a different thing.
Okay, I just didn't know if you could like find power from a confidence interval.
That gets complicated. Don't worry about that for this. Okay.
Stop thinking so hard. I told him to stop thinking so hard.
I like, don't confuse yourself. All right. So if we're thinking about influences on power, like things that go through and start to impact the magnitude of the power of our test, our effect size, okay? Our effect size is the magnitude of the difference between the null and alternative hypotheses in the population. Bigger effect sizes are associated with greater power. Okay, all things being held equal, right? So if I'm got a study and I'm looking for something that's associated with a big effect, awesome. I'm gonna have to have less people in order to detect that reliably. So I'm feeling pretty good about that. My alpha level, if I increase my alpha level, it increases my power. If I set my alpha to 0.10 and I increase my power, this isn't something we can often do because I can't say like, oh, I've decided to publish this and like my alpha is 0.2, right? No one's gonna go for that. But technically, mathematically, if I increase my alpha level, it increases my power, but we're kind of held constant on that. My population variance, variability in the distribution of my sample means increases as my population variance increases. What is the variability in the distribution of sample means? What do I call that? There we go. I love it. Standard error. Yes. Variability in the distribution of your sample means this is your standard error, right? And so as my population variance increases, my standard error increases. My standard error increases. What does that do to my test statistic? Forces it down, makes it harder to go through and test things. Now, we can't control the population variance. Population variance is what it is. But when we're measuring something, now all of a sudden the assessment tools and the things that we are using that can start to impact things, right? So if I'm looking at like say extroversion in college students has some theoretical value in terms of the variance of that of extroversion in the population, right? But if I'm measuring extroversion with an actual like a physical paper and pencil measure, now all of a sudden the characteristics of that measurement start to impact my variability. If I'm just saying, hey, tell me how extroverted you are on a 1 to 100 scale, variability, that's going to be all over the place. Is it a completely invalid measure? Probably not. Is it a good measure? Most certainly not. So if I get a psychometrically sound measure of extroversion and use that, the variability of my sample is going to be sort of much less. So this, we can't control the actual hypothetical variance estimate or variance parameter in the population, but we can shrink that down by using good methods, okay? And then the sample size. Sample size is what we're gonna go through and, oh, there we go, look at that. If we want to increase power, if we need to increase power, it's gonna be our sample size that does it, right? Again, because if I go through and I calculate my standard error, right? Standard error is my variance divided by my sample size, square root of my variance is divided by my sample size. As I jack up that sample size, what happens to my standard error? Drops down. Standard error is smaller. What happens to my test statistic? Goes up. I've got bigger test statistics. I'm more likely to reject the null hypothesis, right? And so your sample size is really the thing that we're sort of that we have the most control over. We can sort of play around with the effect size based on the methodology and do things that are sort of really exacerbating, sort of getting those things to be as different as possible. We can play around with the population variance in terms of having good measurements that decrease variability and noise in there. And so we should be doing at least this, but the sample size is really going to be the thing that probably drives most of our power. Questions on this?
You said that if the standard error is increasing, that makes our, can't remember what you said. You said it has. Oh, the test.
Yeah.
Decreasing.
And why is that going on?
Because you're, I forgot, I blanked out.
No, you're exactly right. Keep saying what you're going to say.
Can you repeat it? I'm sorry.
Yeah, so as my standard error goes up, my test statistic goes down. Why is that?
Because the standard error is the variance divided by the sample size, or the square root of variance divided by the sample size.
Right, and that gives me my standard error. And my standard error tells me across samples, like how much do I jump around, right? But if I think about my t-test, it's the observed difference over my standard error, which is how much I would expect things to jump around. And if the difference that I see in my data is much larger than what I would expect for things to just jumping around based on sampling error, then I'm much more likely to get I'm taking a larger number dividing by a smaller number. It's gonna make my T statistic go higher, which is gonna make it more likely for me to go through and reject the null hypotheses. All right. So, estimating our effect size. If we're gonna go through and we're gonna run power analyses, what I really need is some estimate of effect size in population, okay? Because I can't run a power analysis with it if I don't have an effect size, okay? Existing research, this is gonna be the best source for trying to get a bead on close to the magnitude of effect that we're looking at in the population, right? Like I can't just magic up something out of my head. I have to go through and look through my literature and say, for people who have looked at similar things with this, what types of effect sizes, what size of effect are people finding in the literature, right? This starts to become really important for reporting mean, standard deviations, other relevant statistics. Oftentimes people won't report the effect size for the thing that you actually want to go through and test. But if they've reported mean, standard deviations, other relevant things, I can go back through and take Lindsay's study, because Lindsay wouldn't calculate effect sizes for me, but she was kind enough to give me all the information that I need as a fine methodologist to calculate it myself. And so I can say, this is what I wanted to do, something similar to what Lindsay found in Lindsay's study. This is what I found her effect size to be. And so this is what I'm going to start to be basing my power on. Now, is it great to be basing my power estimate on sort of one estimate of effect size in Lindsay's study?
No.
Probably not the best, right? I mean, it might be fine, but if I had to guess, I might guess that Lindsay studied probably on average is probably overestimated that effect size. And so if Lindsay's study is the only study that I have, that's far better than nothing at all, right? But I should also be careful and mitigate my expectations, because Lindsay's study is just one of a potential infinite number of studies, and I'm not sure where her effect size falls. What's my best bet if I'm pulling from existing literature?
I was just gonna say that it's probably an overestimate.
What's that?
That if you're pulling from existing literature, that it's a bit. It's
Probably
an
an
overestimate.
overestimate, unless what? Like, what's my best recourse?
You like take multiple,
Yeah, and what do we call it if we take multiple studies? What do we call those?
like a multivariate.
Meta-analyses, right? If I've got a meta-analysis on something, right? Then all of a sudden, like, so in my area, like about a billion people have looked at the relation between PTSD and social support, right? That correlation is much smaller than what people think it is. But because there's a meta-analysis that's been aggregated over lots and lots and lots of studies, what I can do is I can say, here's a meta-analysis that's giving me an estimate of this effect. That's awesome. Because then I'm not just relying on Lindsay's studies, I'm looking at the whole literature that someone has synthesized and give me a point estimate of what that effect is likely to be. Now, we don't often have meta-analyses for the specific effect that we're looking for, and then if we don't, then we're focusing on previous research, but this is really going to be our best case scenario. Yeah.
Meta-analysis studies normally have like small participants group of them.
No, they actually, and that's part one of the benefits of meta-analyses is you got essentially you're taking like aggregating all studies that are included in the meta-analysis, and so your sample sizes effectively could be thousands of people.
But if individual ones are small in general, or they don't have to.
They don't have to be. They can be, and you usually have a range of sample sizes in a literature that would constitute running a meta-analysis. Okay, so existing research, this is our best bet in terms of like trying to track down how much of an effect size are we looking for. But if we don't have that, another thing that we can go back to and think about is we can start thinking about how large of an effect do I need in order to make this study worthwhile, right? So in thinking about, okay, my question here isn't, is there a difference? My question is, how much of a difference would I need to be able to detect in order for this to be sort of a worthwhile intervention or something along those lines, okay? And so let's say I'm running an intervention to increase GRE scores. And I say that in order for this to be beneficial and useful for people to do, I need to increase GRE scores by 40 points, okay? If I don't increase GRE scores if I increase it by 20 points, that's fine. but it's not enough to make a practical difference, and so it's not worth anybody's time or money or energy to go through and do things. And so what I can do is say, okay, well, I know that I need to increase GRE by 40 points. And if I know the standard deviation of GRE, take 40 divided by 100, I get a D of 0.4 and say, if this is going to be effective, I need to be able to capture an effect size of 0.4. Okay, so what I'm going to do is I'm going to power my power my study to detect an effect of 0.4. Okay, and if I fail to reject that, because if I run the study and I fail to reject, and it's a type 2 error, because there is a difference between sort of people who don't take my intervention and people who do take my intervention, but it's just the effect size is 0.4, and it doesn't matter because this is what I need to hit anyway. So it doesn't. I don't care if it's not. If it's 0.1 or 0.15 or 0.25 or anything like that. I'm powering it to what I would need to be able to claim a meaningful impact. Okay, so it's a little bit different strategy. So instead of looking through the literature to say, this is the effect that's out there, that is what I am looking for based on previous research. Here, I could say, well, there's no literature out there. No one's run my study before. No one's run my intervention. But in order for my intervention to have practical meaning, I would need to achieve this level. So let me see what that level is, and then I'm going to power it to that. You're just really kind of calling your shot on this.
So like the 40 points, essentially, maybe somebody was like, that's 2 standard deviations above the mean or whatever, and that's
Yeah.
why they arbitrarily chose 40.
Yeah, something like that, yeah. And for clinical folks, like you could do this, right? Like you could say like, hey, in order for this to be beneficial, like let's say I've got an intervention, it's got sort of like a bunch of stuff going on, right? But what I'm saying is like, in order for this to be beneficial, I would need to see an increase or a reduction in scores that's at least as big as the stuff that's already out there. Because otherwise, who the hell cares about my intervention? It's not shorter or cheaper or more efficient than any other thing. We've already got stuff out there that works. So in order for this to be beneficial, it needs to hit at least this amount of difference, because if it's at this or lower, then just use the stuff that we already have, right? Maybe a scenario where this could come up.
I have a question.
Yeah,
How do you determine though that this is what you need to reach? So this is
that's
a
all based.
standard that you put out for yourself?
Yep, it's all based on conceptually sort of your argument about sort of what would be meaningful within that literature. Okay. We could also use conventional cut points. Only when no other options are available would you go through and try and sort of fall back on this. Now this happens sometimes. Maybe there's not. I'm trying to test a theory-driven hypotheses. So practical implications really aren't quite as relevant because I'm just trying to test a component of a theory, and no one has ever gone through and looked at this stuff before. So there's no literature for me to base on. Well, what I can then do is start maybe fall back on saying, all right, what I'm going to power my study, I'm going to power this study to identify, to be able to be adequately powered to detect small, medium, or large effects. And this is what happens. What people will do, and this is not good, like, okay, well, I'm assuming based on nothing that I'm going to find a medium effect. I don't know. Based on nothing, I can hope to find $500 on the ground when I walk home. Like that doesn't help me much. It's not sort of like, I don't know, like I can wish and hope for whatever, but unless I have some basis for expecting this, it's probably not going to be an acceptable way to go through and calculate power. What often happens is that I go through and I calculate sort of how many people would I need to detect a small effect. And that's a lot more people than I can get. So it makes me anxious. And so I'm like, well, what about a medium effect? Yeah, I can do that. So then I'm going to calculate my power to find a medium effect. But if I have no basis for expecting a medium effect, then I'm just doing things to do things. There's no sort of reason to go through and actually expect that, right? Again, when we're talking about our effects in behavioral sciences, what are effects? Probably more than likely, probably small, right? So if this is where you're at, unless you have reason to make a sound argument for the effect that you're looking for is likely something larger than small, you should probably be sort of assuming that you're going to find a small effect and be looking at something probably closer to that level. So Howell in his text says, I don't know, often translates into I haven't thought about, or I haven't thought that far ahead. Less charitable, I think back, I don't know, means I probably didn't try. So just want to think carefully about sort of what you're doing in terms of, so the power analysis is supposed to be a tool to give us, again, an idea, like, are we closer to power of 0.2 or 0.8, right? I personally am less interested in sort of how well your studies are powered, because we're constrained by resources and time and things along those lines. I don't know if anybody wants to complete a 5-year thesis, but at least if you're going in with an underpowered study, going in there with clear eyes and knowing that, yeah, what I'm doing is probably underpowered. But these are the resources I have. And so I'm gonna give it a shot and see what happens, right? As opposed to trying to pretend that what you're actually looking for is a large effect size based on nothing, right? And saying, and then trying to feel, let's try and feel good about my sample of 50 that I've collected to adequately power a detection of a large effect size when there's no reason to believe that that's actually what you're looking for. Yeah, Haley. Oh.
One question, I'm so sorry. My
Oh, you're just rubbing your eye, right? That's what you get for rubbing your eye. Now you need to answer a question that's in your head.
I also had a question. I know I asked one, but.
Oh, yes, Allison, you did have a question.
So like last class when we were calculating like Cohen's D and effects, like how is this, I know you're talking like we would do this before. How is like that different? Or am I not thinking?
No,
of that?
what you're doing when you're calculating your effect size is you're doing a solid to the next person down the road who might look at your study and say, hey, I'm interested in looking at something that's similar to what Allison did.
Okay.
Allison reports, oh, she actually reported her effect size. And so you're reporting your effect size also to contextualize your results, but also for the next person down the road. Like, oh, in this design that Allison used where she's looking at something similar with a similar method, this is what she found in terms of her thing. Cool. I'm just going to hijack that. I can use that as in the calculation of my power.
And are these like strict cut points that like if you have like 0.76 or whatever, would you say large or?
Well, and this is what happens, right? Is so again, like I'm thinking about Alicia's thesis that we're working on, right? So they said, okay, I'm going to collect a sample of 350. It's an online data collection, so she was able to get a lot of people. And so, but she went through and collected some stuff, but some people didn't complete measures. Some people got pitched out because of screening and things like that. So you've got a sample of 350 and you've got 325, right? What we could do is then say, okay, 350 would have got us a power of 0.8. What does 325 get us at? And it's power of 0.78, right? Okay, so we didn't hit our mark, but the impact on our power is probably pretty trivial. And so we can go forward and move forward with that. So these are just general benchmarks, right? So maybe I go through and I say, hey, I've got enough resources to reasonably get 50 people, right? I don't know what effect size I'm looking for, but with 50 people with my design, that will get me, I will be able to detect an effect that is 0.45. And so I'd say something in the small to medium range, right? So yeah, there's no clear cutoff points on this, and you should never use those as clear bright line cutoffs for things. Yeah.
I'm sorry if you already covered this, but like the reason we do like the power analysis before we start data collection is because like it gives us, so you plug in, this is the effect size that I want. It spits out, this is how many people you need. Is that like, I don't know what I'm trying to say. Is that like, we're trying to get that amount of people to get the P, like to get like a small P value, even if there's like a low effect size, we can be like, look at us,
Mhm.
look at our P.
Yeah, okay.
Okay.
So, yeah, no, yes, everything you're saying is
Okay.
correct. You got a little shitty with P's at the end, and that's fine. But so the thing is sometimes, and we'll read an article, about how large effect sizes aren't the end all be all, right? There are some situations and, like some of Sean's work, is pretty cool and like, if I have a minimal manipulation, there's something incredibly subtle and it moves the needle even a little bit. That's pretty impressive, right? And so there, what I might be saying is like, hey, what I'm doing is a minimal manipulation study, and what I'm actually looking for is just consistent with theory. If I do this, this should come up. Now, I'm not looking for a huge effect size, but recognizing that my effect size is gonna be pretty small, I need to have enough people in there to detect it if it's there, right? And so what we're doing with these power analyses is going through and saying, here's what I think I'm chasing down. How many people do I need to detect that? If I want to go up to the Vegas table and win and have it odds of, or a probability of 0.8 of winning, at least, and that's what I assume is acceptable. How many, like, what do I need to gear up to get that, right? And this is where your effect size or your power calculations are coming in. Okay. All right. All right, let's take a break. Let's get back at 3:40, okay? And we'll jump through and keep going with this stuff.
Too quick, sorry.
There we go. All right. Want to quickly introduce this idea of a non-centrality parameter. So our T statistic, right? And here we've got a formula for a one sample T. Our T statistic is going to be calculated right as our mean divided by our sort of minus our value under the null, which is 0 divided by our standard deviation divided by the square root of n. So this is just our T distribution or our T statistic, right? Our T test is distributed around 0 so long as the true mean of the distribution is so long as the null hypothesis is represented the true mean of the population. Okay. So if the null hypothesis is true, we've got our nice central T distribution that we'll go through to use with all our tests that we've been going through and using, and everything is fine and right in the world. Okay. But if the null hypothesis is false, that our actual population value isn't equal to the value specified under the null, then my T statistic here is no longer centered around 0 because we're subtracting the wrong population mean, right? I'm saying the population mean is 0, it's not. And so now all of a sudden what happens is the center of my T distribution, the mean of my T isn't 0, it's something else. It's some value that's not 0, okay? And so what we call that point that where that T distribution is centered is we talk about, we can refer to this as point delta. This represents our non-centrality parameter, okay? And when we take that shift from 0, right, when the null hypothesis is true, if the null hypothesis is true and I calculate T, everything's nice, everything's symmetrical, the mean of T is equal to 0. Sometimes it's going to be a positive number, sometimes it's a negative number, but if the population mean is correct, the mean value of T is going to be equal to 0. As soon as the null hypothesis is not true and we start to get that shift is represented by our non-centrality parameter. And this is so the extent to which that shifts out is giving us our degree of non-centrality with our delta serving as our non-centrality parameter here, okay? So we've got our T distribution that we go through and we look at our tables and everything's nice and centered around 0. As soon as the null hypothesis is true, we still have a T distribution. That T distribution is a non-central T distribution because the mean isn't 0, it's shifted off. And so we can think about power as an issue of how likely we are to find the value of the non-central distribution that's greater than the critical value of T under 0, right? So going back to this overlapping population. So our null distribution, this is our null T. This is our central T distribution that we all know and love. But our alternative distribution that we were talking about, this is actually a non-central T distribution, right? And so if we're thinking about this, our power is the likelihood of obtaining a value in our non-central T that exceeds the critical value of our central T distribution, okay? So what we do is like the null value, the null T, the statistic that we use, and so we calculate probability values and things along those lines. That's all fine and true and good until the null hypothesis isn't true. then the distribution of T statistics that we got doesn't actually represent a non-central or a central T. It's consistent with a non-central T, right? And so this right here that we're trying to find, okay? So just thinking about this again in terms of overlapping population and that non-centrality parameter representing the shift off of the central T distribution. And what do we talk about that shift being similar to or sort of functionally equivalent to conceptually?
Sampling error?
Not the sampling error, because we got a shift. So here's the value assumed under the null, and then so I got, so think about, not quite, it's related to power. What is it? It's my effect size. Non-centrality parameter is a metric of effect size, right? It's how far off sort of my actual distribution is shifted off of that central T. Okay. And this is going to start to become relevant when we go through talking about calculating confidence bounds around our effect size. Okay. So let's go through and sort of go through and pull up your power table that what's that?
What is that little, who's that little guy? Who's that new
Delta.
character?
Which one?
That's delta.
That's, yeah, this little guy with the hat. That's a lowercase delta.
But the big delta is the triangle?
The big delta is the triangle.
Okay.
Yeah, John.
Alright.
When using delta, does any of our assumptions change?
Not for the test, because again, for all of our tests, our test only deals with the null hypotheses. And so all of our T's are working there. So we're not even worried about our non-central T for our hypothesis testing. When we start thinking about power, that's when we go through and start thinking about that non-central T and some characteristics. All right,
What's the name of the
what's up?
power? What's the name of the file? Please, thank you.
All right. So with our single sample T, what we can do is we can start calculating our power by hand using tables provided to us, assuming specific values of my non-centrality parameter and alpha. Okay, so for our single sample test, our metric of effect size is pretty straightforward, right? It's just my mean value, subtract the value under the null, right? Divided by my sample standard deviation. My non-centrality parameter then is equal to my effect size divided by the square root of my sample. Okay. And so let's say that we've got a situation where there's hypotheses that people with higher IQs is like, oh, they're disturbed geniuses and sort of things like that. And so what I want to see is that do people seeking treatment for psychological difficulties have higher IQs? Okay. So I go through and I get 25 people who are seeking mental health treatment, and I measure their IQ, and I get a mean of 105. Okay. Now I know that the mean and standard deviation of IQ scores is 100 with a standard deviation of 15, right? So what I can do is I can calculate my effect size, right? And let's say this is based on previous research, right? So I get 105 minus 100 divided by 15, which is going to give me what? What's that?
What are you doing?
So what's my effect size?
Oh.
Yeah.
What is it?
Negative.
0.33. It is 0.33.
Oh, it's right there on top of it.
There we go.
Yeah.
So I take my effect size of 0.33 and I multiply that by the square root of my sample size. Okay. Which gives me a value of what? What do I get if I take 0.33 and I multiply it by the square root of 25? Danielle, what do I get?
Isn't it 8.25? Well, I just did the square root of 25 first.
Square root of 25 is 5. So
Yeah,
0.33 times 5 is
1.65. Oh.
1.65, that's right.
1.65.
I
Okay.
don't know why.
So there I got my non-centrality parameter. Now what I can do is I can go through and if we grab my power table, okay? When you take a look at your power table and go down through and identify 1.65 on delta. Right?
There.
It's not there, but I got 1.6, 1.7. And I go across and look for a two-tailed test, alpha 0.05. What I can do is I can find my power, right? My power here is gonna be between 0.36 and 0.4. Okay, and so what I can do is I can say my power, if I split the difference, my power is about 0.38. So I can say, assuming that the null hypothesis is false, my effect is expected to reach statistical significance 38% of the time given a sample of 25 and a population of effect of 0.33. People seeing where I got those numbers from?
So
Was that Haley?
okay, so the delta,
Mhm.
all right, okay, that, so I guess I'm not really understanding, so I know that, how do we interpret that piece at all?
No.
Like, okay,
No, I mean, you can think about delta, your non-centrality parameter as like a raw metric of effect size, one that doesn't have a whole lot of meaning to it. So like variance and standard deviation are both measures of variability. It's just standard deviation has more interpretive value. Your non-centrality parameter is just it's just a value that you need to get in order to calculate power.
oh, okay.
Okay.
I have a question.
Yes.
Sorry, so how did you get the
Okay, so this,
power? I get I did the calculation where you get 0.33 times 5 equals 1.650.
okay.
But then how'd you get?
On the power table, they don't
Yeah.
have 1.65, so we went between 1.60, 1.70, and we went to the alpha. And between these two, it'd be 0.38.
Yeah.
Since
Okay,
they don't
thank
have
you.
it.
And so this is what that power table, and this is old school power calculations. This is kind of how we would go through and do things, okay? Now, this is identifying, we talk about this is identifying the power of the test that we did get. Are we excited about power equal 0.38? Probably not, right? That's a pretty poor game we're playing in Las Vegas. Right?
Tomato.
Yeah, lots of tomatoes at that, right? So what I could do is I could say, what's the power or what's the sample I need to achieve a power of 0.80, right? Well, then that's just simple algebra. I just take my power formula here and I just solve for my sample size, right? And if I do that, we get the sample size equal to my non-centrality parameter over my effect size and take the square of that, right? So if I go through and I take 0.28 over 0.33 and I square that, that's going to give me my sample size. Where did I get 0.28?
From the power table?
Yeah, yeah. And so what, Daniela, what does that correspond to?
That corresponds to the alpha of 1.5.
Yeah, yeah. So if I go down and look at alpha 0.05, I found power of 0.8. I look over, it's a non-centrality parameter 2.8, right? Yeah, Gina.
This is kind of arbitrary, but if we have, so we have the non-centrality parameter equation, and then you do some algebra, and then you get the equation you have over there. Are you gonna make us do that algebra, or are you gonna give us the formulas?
Oh, I'm not gonna, don't worry, this is
Okay.
completely new. Don't worry about this for Wednesday. I'm not giving you an
We'll
opportunity to
just like
practice
in the
this.
future.
This isn't gonna be amazing.
Oh,
Need to be on them. It
Well,
depends.
what's that?
It depends, right? I feel like.
Well, yeah, no, I'm not, this is all brand new stuff. I'm not gonna ask you to test it on. I mean, maybe some general concepts, but so these calculations and formulas and things like that, you don't have to worry about this stuff. Okay. Okay, but, no, I don't think, so if you can do basic algebra, so you can sort of move back and forth.
Like, what if you can't?
And so you'll brush up on it. So, yeah, don't worry about that for right now. Yeah. You don't, I mean, thinking about when you're calculating your Z tests and things like that, and so if I'm with that Z formula, right, where you so if this is the Z score and this is your standard deviation, right, then where do you get so you're already doing some of this stuff it's the same type of thing, but yes, no, this is not something that you'll should be asked to do. Okay. So, all right, so if I go through, and so what do I get? 2.88 divided by 0.33 and square that, what value do I get? Everybody should be typing something right now, or at least pretending that they are. What is it?
71.99.
71.99. Okay, so how many people do I need in order to, if I'm looking for an effect size of 0.33, how many people do I need?
72. 71.99.
72, right? We get 9/10 of a person, I don't know who that is, right? So we need 72 people. So if with a single sample test in this thing, if I were to go through and replicate this, I would expect that I would need to have 72 people in my sample in order to detect this effect of 0.33. Okay, we kind of see how we're going through and doing this. All right. Okay, so what about an independent sample team? So independent sample team, here we're looking for the power to detect the difference in sample means. Okay, and so in the equal sample size case, again, here's our effect size. We take sort of mean 1 minus mean 2 over the standard deviation. And then my non-centrality parameter is now equal to my effect size times the square root of my sample divided by 2, where n is the number of cases in either sample. Not your total sample, it's your cell size. But we got equal samples, and so we're even Steven. It doesn't matter which one we get, right? Okay.
If we don't have,
What's that?
if we don't have even samples.
Hold on, we'll get to unequal samples. Okay, so let's say we want to look at identifying the difference in symptom means for treatment 1 and treatment 2. So the difference in means is 5 points, and the standard deviation, we'll call this the average standard deviation of the pool. Standard deviation can literally be average because we have the same number of people there, right? And I got 25 people in each sample. Okay, so to calculate my effect size, I take the mean difference divided by 10, gives me a sample, an effect size of 0.5, right? So I'm saying that there's about a half standard deviation difference between these two treatment outcome groups, right? Take 0.5, multiply it by the square root of 25, which is the size of my sample, my cell, divided by 2. What do I get there? For my non-centrality parameter. What's that?
1.76.
1.76, 1.77, right? 1.77. So I go through and I go down my thing, look, find 1.77. It's somewhere between 0.4 and 0.44, right? So I can say power here is 0.43. So assuming that the null hypothesis is false, my effect is expected to reach statistical significance 43% of the time, given a sample size of 25 per group and a population effect of 0.5.
So why wouldn't you, since there's technically, in this case, 50 participants,
Yeah.
just 2 groups, why wouldn't you just, like, are you wanting to calculate them separately, like per?
No, this is just how you calculate it for the full, for your test, right? Now, why did we divide this by 2? Did anybody remember?
Is that 2-2?
Because it is the formula, that's very true. Two separate groups, right? And when we have 2 groups, what does that do to the estimation of our error? It doubles it, right? Because I have uncertainty in 2 groups, right? So all things being held equal, what are you going to have more power running a single sample test or a paired sample or an independent sample test?
Can you ask a question?
Yeah, all things being held equal, am I going to have more power with the single sample test or an independent sample test? Single sample test, because our independent sample test, I'm taking that and I'm having that, right? Because I've got 2 sources of error and more stuff going in. Okay, so we got this, and then again, it's just rearranging our formula in order to look at the sample per cell needed to achieve power of 0.8, right? So again, I just take this and reconfigure my formula. So I've got my necessary sample per cell is equal to 2 times my non-centrality parameter over D, and square that up, right? So I've got 2 over times 2.8 over 0.5, square that. Someone tell me how many people would I need per cell in order to have an adequately powered test if I'm looking for a sample or an effect size of 0.5. What did you say, Johnny?
63.
63 people per cell, right? So I need a sample size of 126 in order to go through and have an adequately powered test. Okay,
Wait, you need how many?
63 per cell.
63.
So if I double that, that's a balanced design, it's 126, right? So again, starting to think about and thinking about this, like here's a medium effect, right? Medium effect, if I'm looking for a medium effect in psychological sciences, I'm pretty good. I'm feeling pretty good about it, right? If I'm running an independent sample test, I still need cells of about 65 people in order to have adequate power, right? So we can start to see like why in our field so much stuff is underpowered with things, okay? All right, with unequal sample sizes, what we need to do is we need to calculate a harmonic mean sample to adjust for unequal samples, okay? So if I know that I'm gonna have unequal samples, I need to make a small adjustment. And what we're doing here is we're calculating the harmonic cell mean here. And that's just gonna be 2 times cell size 1, cell size 2 over cell size 1 plus cell size 2, okay? And so then what we get, then go through, and then once we have that, then we can go back through and use the same independent sample formula for running this with unequal cells, okay? So if we go back to the Aronson stereotype thread example, okay? And we go through and we say, my control sample has a mean of 9.64, and I got 18 people in that group. And my threat, here's my mean and my sample size in that group. And then my pooled standard deviation, right? What I did is I calculated my pooled variance first, and then took the square root of that to get my pooled standard deviation. Make sure you remember that, that's important, okay? But if I go through and do that, then take the difference in my 2 groups, divided by my pooled standard deviation. This gives me an effect size of 0.99. And then what I'm gonna do is I'm gonna go through and I'm gonna calculate my harmonic cell size, which is gonna be 2 times 18 times 12 over 18 plus 12. Okay, it's gonna give me a value of 14.4. I'm gonna take my effect size, divided by, or multiplied by the square root of 14.4 over 2. What do I get with that? Or my,
2.65.
okay. I got 2.67, but
Yeah.
okay. So close around there, okay? And so if I go down through and I look at my power table, 2.65, 2.67, somewhere around we'll call it 0.75, okay? So again, assuming the null hypothesis is false, my effect is expected to reach statistical significance about 75% of the time, given samples of 18 and 12 with a population effect of functionally 1. Now, something to notice here, right? So if my harmonic cell size is 14.4, right? And I multiply that by 2 because I've got 2 groups. That gives me an effective sample size of 28.8. How many people would I actually have in this sample or in this study? 30, right? What then happens to, what can we infer about the impact of unequal cells on the power of our tests? What does it do? So what I've got going on is I have 30 people in my sample, right? But I'm actually only getting credit for 28.8 of them. So what does unequal cells do to my power? It decreases it, right? So again, thinking about this in terms of, sometimes if we're looking at pre-existing groups, it is what it is. Clinical folks, we have this problem, like I can't manufacture people with PTSD or depression or ADHD or eating pathology or any other such thing, right? I just have to take what I've got, right? But to the extent that we can kind of even these out, it just helps a lot in terms of we can get to more commensurate cell sizes. All right, questions?
Where did you see the 28? Is that from the map?
Okay, so my harmonic cell size here is 14.4.
Mhm.
So basically it's saying that my harmonic size of my cell with this is 14.4. If I take 14.4 and I say, okay, well, I've got 2 cells,
Yeah,
then I get
okay.
28.8,
Gotcha.
right? So this is my effective sample. My actual sample is 30, but my effective sample is 28.8.
Mhm.
It's less than what I had here, so which is, so I'm taking a small hit on my power by having unequal cell sizes.
Now, what if you have, oh, wait, no, so what I mean, independence. So what if you have like another group, you would just throw that one in there too? Like,
Then we've got an annual list.
okay, that's what I was just thinking, I was like, wait.
I have a terrible question.
No, it's probably not terrible. What's up?
So what is our head to know to look at like the 0.05 on the power sheet instead of like the other ones, like based on the questionnaires?
Oh, well, it just depends on what your alpha is. I mean, alpha is almost always 0.05, so
Okay,
we just sort of
but I'm
focus
like,
on that
but
piece.
this will say like alpha 0.05 when you're looking at.
Yeah, I mean, I'll give you your alpha level, because you have to have your alpha level in order to, you have to specify that in order to calculate power. You have to specify one tail, two tail test. All right, finally, paired sample tests, okay? Issue with paired samples tests, in order to calculate power, what we need to do is we need to calculate and sort of estimate the relation between our measurements with a paired sample T, okay? When we're running power for a paired sample test, the extent to which scores at time 1 and time 2 are correlated with one another starts to impact the power of our test, okay? So here, what we're doing, we have to calculate a special effect size for paired sample tests, okay? For a single sample, for our independent sample, we just calculated the effect size that we normally calculate. For our paired sample test, we have to calculate a special measure of effect size that we use for the calculation of power. And so here our formula is mean 1 minus mean 2, right? Like we would normally do. But then we have a special standardizer down here. And the special standardizer is equal to a standard deviation estimate times the square root of 2 multiplied by 1 minus rho, where rho is equal to the correlation between time 1 and time 2. Okay, so if you've gone through and run your paired sample tests in SPSS, it gives you the correlation between your 2 measures, right? This is essentially what we're plugging in here. Okay, and then once you calculate that, then you take that value, divide it by your change score, and that's going to give you your effect size that you would use for your power calculations.
What does T1 and T2?
What's that?
T1 and T2?
That's time 1 and time 2.
Oh.
Yep. Okay. So remember when we were going back through and we were working through our paired sample test, and I gave you that D repeated measure up there in the corner. That's what this is for. Okay. So I mean, if you see this, I mean, we've got the same stuff going on here. I don't like this as a measure of effect size for paired sample tests if it's going to be something you report, because what happens is that effect size is probably going to be a lot bigger than your glasses delta or your standardizing using the average variances across time 1 and time 2. We're already concerned about inflation of effect size. What ends up happening is when you go through and adjust for that correlation, it makes that larger, which is nice to look at because it's bigger. But if I'm just reporting that, I'm probably reporting an overestimate of what people are expecting to happen there. Other thing too, I don't know how to give an impractical interpretation of that, right? I can say that yes, based on variability at standard deviation of baseline, I'm seeing about a 0.8 of a standard deviation increase relative to variability at baseline across time and time one and time two. I don't know, that's got a denominator packed in with a radical and an absolute value and a correlation, like I don't. This doesn't have much interpretive meaning outside of just a number, right? So you will see sort of this reported as a measure of effect size for paired sample tests. Helpful for the calculation of power, probably less helpful for reporting, unless you just want to report the biggest effect size that you can. Okay. Yeah.
Who's this new character? It looks like a P, but
Looks
it
like
doesn't
it's
feel
Rose.
right.
That's Roe.
Okay,
Ro's a good character. I like it's like a P, not a P. Yeah, so yeah, that's just your lowercase rho right there. And so this is just Greek notation or statistical notation for a population correlation.
And row as in like ROW, ROV.
RO.
RO, so it'd be right, okay.
Yeah.
where,
You don't worry about that. I'm not gonna test you on.
where is the row coming from? How do?
So this would just be, we will almost never know the population correlation between time one and time two. So like anything else, we're just substituting our sample correlation. So the correlation of time one and time two. All right. So let's say we take that Arnson study again. So last time we talked about using that as an independent sample test, which is how they ran it. Like, okay, we have people completing the exam under threat and people are completing the exam just without a threat. But let's say that we go through and we change this around. And what we do instead is we have people come in and we go through and we measure people once under a threat condition and then maybe have them come back, say a week later, and complete an alternate form of the test that's equivalent under a no threat condition, right? So we changed the design. Instead of having an independent sample test, now we have a paired sample test, right? So everybody gets to serve as their own control. So what we find that the difference at time one, which is the control condition, is 9.64. And in the threat condition, the second time we bring them back, it's lower, 7.55. It's not as low as it was in the independent sample test, but it's still, so we're seeing a reduction consistent with stereotype threat. But we've only got 30 people in this whole sample, okay? My pooled standard deviation across the two time points, 0.31, test retest is 0.92, okay? So these two time points are very correlated with one another, okay? So I go through and I calculate my standardizer. Take my standard deviation, multiply that by 2 times 1 minus my correlation between the two time points, right? And this is going to give me a value of 1.24. I go through and I take the mean at time 1 minus the mean at time 2. Go through and divide that. Where do I get as my standardized or as my effect size estimate?
1.69.
Yep, 1.69. Okay, so to calculate my delta, I take 1.69 times square root of 30.
9.26.
9.26. Okay, where did I get that? Where did I get that equation to get delta out of that?
From our single sample delta.
Yeah, it's my single sample, right? Because again, that's all a paired sample test is from a calculation standpoint. It's just a single sample test with change scores, right? So I calculate my delta the same way. I go through and so I get a delta value of 9.62. Is that even on my power table? No. What that means is my power is off the charts. Okay. I say I have over a 99%, like basically I have perfect power here. Assuming that the null hypothesis is false, my effect is expected to reach statistical significance over 99% of the time, given a sample of 30, a correlation between repeated assessments of 0.92 and a population effect of 1.7. Yeah.
With the test retest value, we're not calculating that at all. That's like a given value.
typically?
The row?
No, we would calculate that, but that's based on probably a couple of different things. We can talk about the test retest, we can use that. What this is generally gonna be is the correlation between time 1 and time 2 on our sample.
Okay.
But if we have a metric that has a strong test retest that's consistent with what just known psychometrics, we can go through and substitute that in there. So there's different sort of, we just want to see like across repeated assessments, what's the correlation of measures here? So Kate, that could come from a number of different cases. If it's my own data, I can just calculate that directly, right? But if I'm trying to power my test based on something that someone else has done, what I would probably do is look at for a test retest value for whatever measure we're looking at. Yeah.
So our power is off the chart like this one.
Yeah.
Cause we can't see it.
Yeah.
So. So that means that. So does that mean that like we are all good? Like how do we interpret?
Yeah, we're just gonna hit home runs, right? It's gonna, with this design and this sample size and this effect size, it's gonna be hard not to identify this effect.
Okay, so that means that we definitely have a statistical significance.
We might, and so again, assuming that the estimates I have are reasonably close to the population effects, then sure, right? But there's a possibility that wherever I'm drawing this is actually sort of not actually representative. Let's say that the actual population effect based on this is actually equals 1.0, right? I just happen to get an effect that's sort of out here.
Yeah.
Now all of a sudden I'm powering something to this effect, but this is the actual effect. And so there's always uncertainty there, right? All of my studies are always fallible all of the time. Now, this is the best information I have to go on, then that's fine. But remember when we talked about the problem with our null hypothesis testing, right? Is that probably the stuff, just because we don't publish null findings, only those findings that get past that p less than 0.05 value are the things that get published. And probably what's going on, at least in a fair number of those cases, that these are studies that aren't necessarily bad studies, they just fall on the end of the tail, right? But if this is the only one that gets studied, that gets published, and nothing else gets published, then we have no reason, there's no way of knowing that the actual real effect is probably down here, right? And so we always need to be careful and to recognize that, and again, this is why I'm said at the beginning that calculating power it's much more like horseshoes than darts, right? It's not super specific. We're just trying to get a general guesstimate of where we're at with things. Okay. Yeah,
At the
okay.
beginning, you mentioned that power greater than 0.8 could be, like potentially warrant like, or have unwarranted conclusions.
Yeah.
Like we're essentially, we're like overpowered essentially.
Yeah, and so that can't happen, right? In this case, I got 30 people. That's probably not a huge burden on me or participants. The other thing too, thinking about like, and this is me talking from like an ethics IRB standpoint, if I'm having people go through and putting them through a lot of stress or something that's could have sort of potential sort of harm if I'm not, so like, we're gonna do everything we can, but there's some risk associated with participation in this stuff. Like ethically, I should only take or measure or think the number of people who I actually need to detect the effect, right? And so if I'm running some test that is dangerous, like, oh, I'm just gonna get 1 million people, and that way I sort of really get a precise estimate. It's like, well, one, a lot of time and resources and effort on your part, and then two, also we're asking a bunch of people to go through and assume risk to participate in research that might not be warranted. And so thinking about that. Other thing too, if I have like a sample of 1,000 or 1,500 or something like that, potential for me starting to make unwarranted claims about correlations between variables when in fact it's just all driven by power. So yes, we can have overpowered things. Here I wouldn't be too worried about it. just given the circumstances, but again, it all kind of depends on context.
So if like the N was like 1,000 and we had like a 0.99 power, then you might be a little bit more.
Yeah, you might say back, okay, maybe we can scale back on the number of people we need for this replication or something.
Okay.
Yeah. Andy, did you have a question? Last question, what's going on with power in this sample? Or within this example here? Okay, remember that when we went through and we looked at this Aronson example where we had 30 people, I've got power of 0.75, right? But if I went, and so if we're looking at here, we've got a mean between the control and the threat of, 9.64 to 658. Here, we ran this as a paired sample test with less of a difference, same number of people, but less of a difference across the two measurements. But this time our power is through the roof, right? What happened?
It's within subject.
Yeah, so within subjects, okay. A couple of things. One, we're adjusting for the relation between those two measurements. And as that measurement increases, things are gonna, as the association starts to increase, my power is gonna increase. Other thing too, when I'm calculating with a paired sample test, how many sources of variability are we having to account for? Just one, right? All of this to say, so we can say here, even though we're finding a smaller sort of mean difference across these, our power is hugely up through the roof, right? Repeated measure designs are gonna have far greater power with smaller differences than our between samples tests, okay? So again, here's our calculation for the calculation of power. Here's how we're getting our effect size, right? And what we're doing is we're accounting for that correlation between our repeated assessments, okay? What we're doing is with our repeated measures designs, we're parceling out participant level characteristics, right? So let's say I'm measuring, I want to measure mood, right? Of people sort of on Monday and on Friday, right? What I could do is I could have everybody I could get a sample of people measure their mood on Monday. And I grab another sample of people, measure their mood on Friday, right? And sort of see if I see differences there. That's my independent sample test. Problem is that I've got different people in one group versus the other, right? And so what I might find is that, so let's say Mandy's in group one and Mandy's a pretty miserable person. Mandy always sort of rates her mood as bottom, but it doesn't really matter where Mandy's actually at. Mandy trends low on this mood rating versus Allison is always through the roof. She's very high, things along those lines. Now, if you go through and I measure you in different groups, there's all that difference in terms of where things are going, right? But if we run this as a paired sample test, right? Now, Mandy is measuring her mood on Monday and on Friday, same with you, right? And you can be at very different levels individually, but within sets, if each of your mood increases by about 2 points, all we're looking at is the increase in mood, not where you're at, right? So there's much less variability because everybody's existing as their own control. So what we're doing is we're cutting out that systematic between participants variable there. And what we're doing is we're reducing that overall noise, okay? And the correction to my standard error is going to be a function of the correlation between my repeated measures. My effect size and my power is going to increase as rho increases, okay? So as the correlation between my repeated assessments starts to increase, the power of my test starts to get higher and higher and higher and higher. Has anybody done like physio types of stuff before, like physio research? We get physio measures if we're looking at things like skin conductance, heart rate, and things along those lines, right? Like, I mean, I only have so much variability in my body from wherever I start and where I think lots of very different variability across people, but within people, where I start and where you measure me 2 minutes from now are going to be highly correlated. This row can be like, if it's collinear, it's like 0.98 with one another. my power goes up through the roof. Cause I get even any deviation, right, across what's going on, it's gonna start to pick that up, okay? So as the correlation between my two measurements starts to increase, my power starts to increase. As my rho coefficient starts to get closer to 0, as the measurement of time 1 versus time 2 starts to get equally unrelated, essentially what I've done is I've sort of broken this down to an independent sample test. Because my measures at time 1 are functionally unrelated to my measures at time 2, I miss out on a lot of that power stuff that's going on here, okay? So this is why, in terms of reporting this effect size as a measure of effect just with the standard tests is not good, because particularly as that correlation starts to increase, that's going to get increasingly inflated, which is great for power and sort of identifying a statistically significant effect. But in terms of an actual measurement of like how closely those are, how much of an effect to expect from a practical standpoint, sort of interpretation things start to get problematic, okay? So moral of the story, anytime you can use a repeated measure design, it's a good idea. If there's any way to work that in and have a repeated measures component, your likelihood of obtaining effects starts to go up through the roof. There's some stuff that we have to address when we have a repeated measure. It's a little bit more complicated, but the benefits in terms of power are huge, okay? So always be thinking about that in the back of your mind when you're developing your studies and things like that. Can I incorporate a repeated measure or a repeated measure in there? And if you can, if it makes sense, it's definitely worth trying to get worked in. All right. Power calculations with G-Power, okay? This is a free online tool that you can go down through and download and sort of go through. It's fantastic. It's easy for simple power calculations. You start to get more complicated. It won't do everything that you need. Dr. McCrae and Dr. Wachowski have beef with G-Power, and sort of rightly so. But for simple types of tests and things like that, it works fine for doing some power calculations. So here's the site. You can go down through, get that, and download power for our single sample t-test, right? Or excuse me, our single sample test. What we can do is you just go to your t-test family, so pick t-test, difference in means from constant. So we got a 1 sample test. Looking at a priori, we're looking at computing sample size based on alpha, power, effect size. Here we want a 2 sample test. For my effect size, I can hit determine, right? And go through and it'll ask me my mean under my null, my mean under my alternative, my standard deviation. We'll just calculate an effect size for you. You can calculate transfer main window, just pitch it back over there. So you can do this, or if you've already calculated your effect size, based on like an example, you can just drop that in there for that. Your alpha level, make sure that's 0.05, power 0.8, you go through and calculate, and it's going to give you your power right there. Okay. So pretty easy to go down through. Biggest thing to make sure that you're doing probably is that 2-tailed test. That's default to 1, just make sure that you got that on the right thing. We got an example here, but this is just basically giving excuses for numbers to plop in there, right? So pretty straightforward. Same thing with our independent sample test. Again, it's gonna be a t-test, but here we're gonna look at difference between 2 independent sample or independent means or 2 groups, type of power analysis. Again, we're just looking for our sample size here. So again, this is telling you you need 65 people for that to adequately power this test here, okay? Here, we put in our effect size. Here you can do a couple of differences. Here, if you can go through and calculate mean group 1, mean group 2, standard deviation 1, standard deviation 2, and then hit calculate, and that'll give you that. But if you've got differences, well, you're just looking at population or sort of estimates here. So you can go through, use this to calculate an effect size, drop that in, again, a 2-tailed test, 0.05, power 0.08. This is your allocation ratio. what this is saying is it's accounting for unequal samples, right? So what's the ratio of how many people you have in sample one compared to sample two, right? So 4 would say I've got 10 people in sample in cell one and 40 in the other, right? If you have equal levels, what would you go through? Be 1, right? Because it's a 1-to-1 ratio, right? So if you have equals, put in 1 there and go through and calculate stuff. So in this case, what it would say is if I have a 4-to-1 ratio with given this effect size, alpha 0.05, I want to achieve power of 0.8. I would need 10 people in one group and 38 people in the other for a total sample of 48 if I'm expecting that much of an imbalance. Okay. Paired sample T, same thing. Here we're just selecting the difference between 2 dependent means, a match pair, effect size. Here we've got mean group 1, mean group 2, standard deviation 1, standard deviation 2, correlation between groups, plug that in, hit calculate, that'll zip that over to there. Alpha power is generally going to be 0.8. So here, if I'm looking for an effect size of 0.7, I need 18 people in my sample in order to achieve adequate power.
Sorry, can you go back one slide real quick?
Yeah.
The allocation ratio, being 4, I'm struggling with it. Can you explain that again?
So if I'm expecting unequal samples, right, I can say unequal samples decreases power, but if I can only get 10 people in one cell, that doesn't mean that I should try and match it because then I'm only gonna have 20 people. I should still try and get as many people in the other sample just because that's gonna be a far bigger impact than sort of making sure they're even Steven, right? So maybe in a situation, Katie, where I was saying, I am expecting, I can get probably 4 times as many people in this control group as compared to my clinical group. That would be what you were doing there.
So it's
If-
4 times.
4 times,
Okay.
yeah. And if you can see that, you see that it's about a 4-to-1 ratio there. So just going through. And so if we're going to go through and have an equal samples, we'll just put that as 1 and then that would fix that. Okay. All right. So we got that. Okay, there we go. Right up. Okay, so again, just a quick effect size or power right up here. Effect size D equals 0.45 was expected based on existing data from Jones and colleagues in 1980, right? Power analyses in these data indicated a sample of 32 individuals per group who would be required to achieve adequate power at alpha 0.05 1 minus beta equals 0.8. So right up is just pretty quick. It's just saying big thing here is identifying what effect size that you think that you're going to be chasing down based on what, and then how many people do I need for the sample in order to achieve that. Questions? Feeling okay about this? Okay, so probably what I wanted to do is go through and have you, and I will in this assignment, have you go through and calculate, do some power calculations by hand, just so you have an opportunity to kind of see where that's coming from, but rarely do we now do power calculations by hand. So G power is probably going to be for these simple pairwise mean sample tests is probably where you're going to be calculating your stuff. All right. Conceptually, wanted to think about, so what happens if I go through, I do my due diligence. Basically, you've gone through, you've looked at previous research and you've got an estimate of so what you think your effect size should be. And maybe even you've got there's a couple of studies and you go through, maybe calculate, use a couple of different estimates. You make, okay, I think this is the sample size that I need to adequately power my test, right? And so you go through and you collect that sample, and then what happens is you go through and you still fail to reject. You run your thesis and things come up null, okay? Question is, what happened? That probably shouldn't have happened, right? If I've gone through and done all my homework and legwork to go through and run a real good power analysis for this. But then I still sort of come up no results, right? How do we go through and understand like what's happening with this? Well, one, I might have had an error in my power calculations, right? I might have made a mistake somewhere and sort of thought it was this, and so I got some mistake there. That's pretty low level stuff, right? Other thing that could happen is that my effect size is smaller than sort of what I had thought it was gonna be, okay? Should we expect that this is a possibility? Yeah, why is that, Kate?
Existing literature
Yeah.
and the bias of publication.
Yeah, so that publication bias and things like that that we talked about, right? You know, if I'm looking at, there is a small effect in the population. And lots of people are trying to get at it, but one person does, like Lindsay gets it, right? But Lindsay just on accident happened to wildly overestimate the effect size. Her study gets published, but everybody else trying to get their study published with 50 people are failing to reject the null because the effect size is considerably smaller than what Lindsay found. But everybody thinks it's this, and so this is what we're all chasing. And so then there's 15 studies that have failed to find failed to find evidence of effect, but everybody's using Lindsay's study based on that, right? So we could have, there's a very real possibility that effect size estimate is too small, and you put an inflated effect size estimate in your power estimate in your power calculations, and so it's going to tell you you need a smaller sample size than what you actually need, and so you collect the sample size you thought you need, but you still have an underpowered study because the effect size is wrong, right? That's a big possibility just based on what's going on. If we can find some sort of meta-analysis, that's awesome, because then that hopefully is going to be pulling in not only stuff that was published, but unpublished stuff and aggregated things across, but it's still a possibility, right? Other thing, we might just have a type 2 error, right? Sometimes we just swing and we miss, right? Even if I step up to Matt's table and Matt's the dealer and it's a really good game because I've got an 80% chance of winning, doesn't mean I'm gonna win all the time. Sometimes I'm gonna swing and I'm gonna miss, right? So if I power something to power equals 0.8, 20% of the time I'm still gonna miss just because I'm gonna fall in this area, right? And so even though the null hypothesis just sort of basically I've got a type 2 error, essentially, right? Now, mad. Thanks. There's no way for me to go through with the data that I have in hand and know which one of these things is going on. I guess I can go through and check my power calculations, right? But this is the frustrating piece about research is that we don't know, right? What we can do is if I go through and I sort of run through and I look at the effect size, basically you go through and you look at the effect size that you did calculate, and it is quite a bit smaller than Allison's. You might say like, well, it's possible that she might have overestimated that effect just sort of through no fault of her own, but it's an overestimated effect. Or maybe mine is just an underestimate. I don't know, but just trying to go through and sort of think about like what's happened with this, because this will happen, even though I sort of do my best to go through and calculate power. Again, we're talking about horseshoes, and so there's still lots of room for error. Okay. Last thing we'll talk about here is something called observed power. Okay. Now, generally, what we're doing with our power calculations is we're trying to predict something and plan something about a future study. So, Jalen, you're talking about like, so why would we go through and do this? What we generally want to do in using this is most helpful is I've got a thesis, I've got a dissertation, I've got a grant proposal or some lab study that I'm really wanting to do. I want to give myself the best opportunities to find this thing. And so what I'm going to do is I'm going to calculate my run a power analysis to see what's going to go on in this study that I have planned. Using these procedures to go through and look at the power of data that you've already got is not going to be a helpful thing, okay? What happens, and SPSS will do this, there's an option for a thing where I can go through and tell it to give me observed power, okay? And so the idea is that, boy, if I've got an adequately powered system, Jalen, you did your homework on the front end, and you did all the, and so you adequately powered your study, right? And so the idea is that, boy, if I have an adequately powered study and I still fail to reject the null hypotheses, then that maybe indicates that the null hypothesis is true, right? If I had adequately powered this study and I still fail to reject, maybe the null hypothesis is true then, right? If I do this. And so what maybe, hey, what I can ask SPSS to do is give me an estimate of the observed power. Because if the observed power in my study is calculated by SPSS is 0.9, and I still fail to reject the null hypothesis, maybe that means that the null hypothesis is true, right? Seems like reasonable logic, right? Problem is that the observed power that SPSS or these programs is calculating for you is a direct function of the p-value. Okay. So if I get a p-value that falls above 0.05, by definition, my observed power will always be low. There is no circumstance in which I can fail to reject the null hypotheses and have that observed power estimate be high. What's always going to happen is if I fail to reject, my observed power is going to tell me my power is low. And so this idea of this, where I'm going to have a result where my observed data is going to tell me I have an adequately powered study, but I still fail to reject the null hypotheses, is mathematically impossible. It can't happen. Essentially, observed power is just redundant information. Your observed power is just going to, if you have low observed power, it just tells you that you failed to reject the null hypothesis. So, and this Honig and Heisey paper here is brilliant in terms of just like walking through, like, it's functionally a useless statistic. Like, it tells you nothing that you couldn't already identify with the p-value. What you want it to tell you is not what it's actually going to tell you. Just kind of a theme in statistics, right? And so just knowing sort of the trap that you fall in and sort of not saying back. Or if you go through and you say, oh, well, I failed to reject the null hypotheses. Maybe it's because I have not an adequately powered study. And yeah, look at some of my study was underpowered. So yeah, it definitely says that if I would have gone through and collected more people, then I would have found this effect. Again, that's always going to happen. Like, it's tautological, it's circular, right? Because by definition, if I failed to reject the null hypotheses, it's going to tell me I have an underpowered study, right? So there's really no new or useful information within this. So again, because observed power is determined completely by P, there's no useful information that I can use to go through. It's similar to sort of my peeve about, not a peeve, a thing that I'm sort of not wanting you to do is say, oh, I rejected the null hypotheses. Also, my confidence bound didn't include the null value, and therefore that's additional evidence against the null hypothesis. Like, no, it's not. It's all the same thing. Like, it's not new information. Like, those two things can't be discriminate or be different. They have to be the same because they're all using the same numbers. Same thing with this. Okay, so just be aware. Again, this is a fantastic paper. So definitely go through, make sure that you go through and read this, but just recommending or identifying the problems with that observed power button that you can click. I don't know, do it if you want to. It's just not telling you anything useful in terms of meaningful results. All right. Let's jump in and finish up with an initial talk about confidence intervals on effect sizes with this. I guess any final questions about power? Power is a crazy concept and it's kind of hard to wrap your head around, but once you kind of got a handle on it and sort of understand what's going on, really helpful in terms of thinking about how to interpret null effects and sort of kind of put things into place and thinking about powering studies and planning studies and stuff like that. Okay. Confidence intervals on effect size. We're calculating our confidence intervals like you all have been doing around mean values and mean differences and things along those lines. What we've been doing is we've been using a central t distribution to go through and calculate those, right? So we have our mean value plus or minus my t critical times my standard error, right? That's my confidence bound for mean differences, right? And what we're using here for this t critical, we're using our central t distribution, right? This is our T distribution on our books and our tables and things along those lines. Our central T is symmetrical. It's centered around a value of 0. And it's completely defined by my degrees of freedom, right? If I want to know what central T distribution I'm looking with, all I got to do is I got to go through and find my degrees of freedom. That's going to tell me exactly what family of T I'm working with, okay? And my null hypothesis testing using my central T distribution is assuming a population value of T equal to 0, right? And this is sort of when we use our T critical and our P values, it's all working with our central T distribution. Okay. But if I'm trying to calculate a confidence interval around an effect size, okay, what I've done is if I'm calculating a confidence interval around an effect size, if I have an effect size, the assumption is that my effect size is not 0. The assumption is my effect size is something as opposed to nothing. And so if I assume that I have an effect size where my mean relative to my null is not equal to 0, now all of a sudden what I'm having to do is I'm having to shift over to the non-central T distribution. Now remember when we were talking about power, we were talking about that shift between your central T and your non-central T. Central T distribution is fine for the distribution of your T statistics so long as the null hypothesis is true. As soon as the null hypothesis is not true, now you have a different T distribution. This is your non-central T. And that shift, right, from the 0 to wherever your T distribution is now centered, that's your non-centrality parameter, right, which is a measurement of your effect size, okay? But so now what we've got is we've got a non-central T distribution, but also as we go through, we shift that central T off, right? As soon as we include that non-centrality parameter, the shape of that distribution starts to change. It's no longer symmetrical, right? As we start to shift off into our non-central T distribution, the distribution of our non-central T's are skewed, okay? And what we do in order to identify and sort of define and capture that non-central T, now we've got 2 parameters to think about. We've got our degrees of freedom, but also our non-centrality parameter, right? So our questions are, in order to define this distribution, we need to know what our degrees of freedom are and how far off of 0 that T is shifting, okay? And so, again, thinking about degrees of freedom and non-centrality parameter, and notation for non-centrality parameter, we talked about it as delta, be large, capital delta, it could be NCP. Notation kind of bounces around. You just have to sort of make sure that you understand what they're talking about here, okay? Our non-centrality parameter gives us the point at which that non-central T is shifted to the right or the left. And again, that non-centrality parameter, again, is a sort of raw measure of effect size. It's going to tell us, give us an estimate for the difference between the true mean and the mean under the null hypothesis. Okay. And because our effect sizes that we go through, we report are a linear function of the non-centrality parameter. If I can generate confidence intervals around that non-centrality parameter for the non-central T, what I can start to do is I can start to get upper and lower limits for my effect size, okay? So this is what makes the calculation of effect sizes or confidence intervals for effect sizes a little bit more different, because we have to use a different distribution than our central T that we like, right? Because what we're doing is we're talking about a shift. Now all of a sudden we've got a non-central T that's non-symmetrical, that's defined by 2 parameters, your degrees of freedom and your non-centrality parameter. So there's more things to go through and come into play. Yeah, and again, Wilkinson making a strong argument for the inclusion of confidence bounds for effect sizes. We'll talk about some of the pros and cons of this. Okay, so if you're thinking about non-central T distributions, non-central T is centered at your non-centrality parameter, can take on any positive or negative value, right? It can be sort of anything, sort of the positive to the negative. It's that non-centrality parameter is just telling you how much of a shift that you have from the central T distribution, okay? With a non-centrality parameter at 0, now we're just back to our central T, right? That we all know and love, that's all nice, right? But we know about our non-central T. We know that our non-central T is a skewed distribution. And that skew gets pretty strong at low degrees of freedom, okay? If I've got a low degree of freedom distribution, skew of my non-central T is gonna be pretty severe. As my degrees of freedom increase, it's gonna start to get sort of better, but particularly at low degrees of freedom, it's gonna be relatively skewed. And as my non-centrality parameter increases, it's gonna start to get increasingly skewed. So as my non-centrality parameter increases, what does that indicate about my effect size? That my effect size is getting bigger, right? And so as I'm looking at trying to calculate confidence bounds around large effects, that distribution is going to start to get really skewed depending on sort of which way we're looking at stuff. Okay. Now, as my degrees of freedom get bigger, it starts to reduce the level of that skew, but it's still going to continue to be skewed even as my degrees of freedom increase for that. So my approach to an asymptotic value is very, very gradual. Okay. And even our small values or distributions associated with small degree non-centrality parameters, even if I have a small effect, I'm still going to maintain a noticeable level of skew even with relatively small degrees of freedom, or even with relatively large degrees of freedom. Okay, so basically what we've got is we've got our central T distribution, right? But as soon as the null hypothesis isn't true, what we're talking about is a shift relative to the assumed value under the null. And as soon as we do go through and do that, we just have kind of like a stretch arm. We start to stretch that distribution around. And so it's no longer symmetrical. It starts to get stretched on one end and shorter on the other end. So thinking about what we know about confidence bound, what's that going to do to our confidence bound? It's not going to be symmetrical, right? Our point estimate isn't going to be dead center in the middle. We're going to have an upper bound or a lower bound that stretches out farther than the other one. And so now we've got a non-symmetrical distribution, which is going to give us non-symmetrical confidence bounds. And then we also have to find point estimates and confidence bounds around a non-centrality parameter or non-central T. All of this starts to get pretty complicated really fast in the absence of elevated levels of computation. Okay. So the computation of our exact non-centrality parameter is complex. There's not a formula that I can go through and give you to go through and do this. It's complicated, right? And before increasing computing power, what we used to have to do is sort of extrapolate this from tables, from central T distributions, which is kind of a pain, okay? And even when I started teaching this class and was trying to figure all this stuff out, what it ended up with me in program R, sort of iteratively like entering values to try and get sort of upper and lower limits and things like that. It was a hassle. And if it's a hassle, people aren't going to do it. And this is why you don't see confidence bounds around effect sizes very often, although it's starting to become more common. But what we've got now, people started to recognize that this is an important thing. Different tools for going through and calculating that non-centrality parameter. Okay, this here is a tool by Steiger. Okay, now for you Apple users, for you Mac users, this for some reason won't work properly or hasn't worked properly. I don't know. If you want to use this, you may have to get a real computer and sort of try and go through like Apple and do everything except the actual work that you need to do. But essentially, so if you go through, it's just a nice little tool. And here, what we're going to do is you're going to get your non-centrality parameters. You're going to indicate what distribution you're looking at here. We're going to say a T. And then we want to calculate a 95% confidence bound. We're going to enter our test statistic, our T value, and our corresponding degrees of freedom. We're going to hit compute. And what it's going to do is it's going to give you an upper and lower bound for your non-centrality parameter. So for a test statistic for a T value of 6.78 with 43 degrees of freedom, this is giving you an estimate of the non-centrality parameter, a lower and upper bound for that non-centrality parameter. Okay. But what do we say non-centrality parameters represent?
What's the question?
What does the non-centrality parameter represent? A measure of effect size. So if I have an upper and lower bound of the non-centrality parameter, what do I have? an upper and lower bound of our effect size, right? And so then it starts to be pretty easy to go back through and calculate our upper and lower bounds for our effect sizes, okay? So for our single mean, for a single sample test, if I just take that, the lower bound of my non-centrality parameter divided by the square root of n, I get a lower bound for D. If I take my upper bound of my non-centrality parameter divided by the square root of n, I get the upper bound for D. Okay. Same thing with my independent sample test. Take my non-centrality parameter, multiply it by 1 over the sample 1 size plus 1 over sample 2 size, take the square root of that, gives me my lower bound. Do the same thing for the upper bound, gives me my lower and upper bound for my T. My repeated measure, again, if I take the lower bound and upper bound, can go through, I mean, it's the exact same thing as my single sample because a paired sample is just the same thing as a single sample. Only thing to note here, and this is true for if you're calculating this by hand for any of your tests, right? What did I need to enter in order to get my non-centrality parameter in that Steiger calculator? What did I have to put in to get that upper and lower bound for my non-centrality parameter?
You know, the L, like the law,
What's that?
the law? Nope.
What was it?
It's your T value and your degrees.
My T value, my degrees of freedom, right? So my non-centrality parameter is based on my T statistic, right? And so what that means is whatever, when we are calculating our effect size, we have an option in terms of standardization, right? But if I'm wanting to calculate by hand a confidence bound around my tests, around an effect size, the effect size that my point estimate of my effect size, whatever I use as the standardizer, the variability estimate that I use for the standardizer needs to match up with whatever it was with calculating my T, okay? So for my single sample, it's just my sample variance, right? For independent, gonna be my pool, right? Now, here, if I go through and I use like glasses delta or something like that, my confidence bound for glasses delta, if I go through and just use this procedure, it'll probably capture it. But it's technically not the right one because what we're doing is with this procedure, we're calculating a confidence bound around an effect size using my pooled standard deviation as the standardizer, which means it's my hedges G, right? But normally with this stuff, you won't identify or see too much of an issue until you get to paired. What standard variability estimate are we using in the calculation of our paired statistic? Standard deviation of what? Standard deviation with change scores, right? And so the variance of my change scores. Now, the variance of my change scores can be very, very different than the variability at time 1 and the variability of time 2. What will happen is if you just go through and like calculate the glasses delta for your paired sample test, which is a wonderful and perfectly fine metric of effect to measure as a point estimate. And then I go through and I enter my paired sample T in degrees of freedom and get my upper and lower values for my non-centrality parameter. What will happen is I'll often end up with an effect size that doesn't fall within my confidence bounds, right? So if I'm going to do this by hand, my effect size, if I want to calculate a confidence bound around my effect size for my paired sample test, what I need to do is I need to use the standard deviation of my difference test as the standard deviation of the difference as the estimate of my as my standardizer, okay? Because otherwise what will happen, or the standard deviation of my difference is my standardizer. Otherwise what will happen is I'll end up with a point estimate that doesn't fall within the bounds using this procedure. Now, SPSS goes through and calculates confidence bounds around different measures of effect for paired tests. I'm not exactly sure how it's doing that. I'm assuming it's probably fine. Now that's not 100% safe assumption, but if you're doing this by hand, sort of know that for your repeat measures, the standardizer that you need for your point estimate is gonna have to be the standard deviation difference test. Okay. Or standard deviation difference. So last thing here is what we can do if you really want to get, if you really want to go over the top in terms of your power analyses. What you could do is you could take the point estimates you found in the literature and then go through and calculate a confidence bound around that effect size that you found in the literature. You can find a lower bound and upper bound and use those lower bounds and upper bounds to calculate estimates of the number of people that you would need. You'd say, hey, Haley's study supports, like, this is her point estimate for the effect that she found there, but the lower bound is this. What I'm gonna do is I'm gonna calculate the lower bound of Haley's effect size. And I'm gonna run a power analysis based on that lower bound estimate to see like what is, at least based on the, what's the highest number of people that I would need. Okay, so lots of things that you can go through and start to go through and play around with this stuff. Okay. All right. Boy, we almost got all the way through that. But we're in a good space. So in terms of your exam, okay, this is stuff like we haven't had an opportunity to go through and talk about or have you go through and test and sort of run through and stuff like that. So I'm not going to ask you to do calculations or anything like that from this, but do generally kind of make sure that you're understanding sort of general concepts and things along those lines. One, it'll help reinforce the other stuff that we've already done and sort of make sure that you're good there, but don't panic or think that, oh no, Josh is going to make me sort of run algebra on a power calculation, work backwards and stuff. We haven't had an opportunity to practice this, so it's not fair to then just throw you in the deep end with stuff. So generally sort of know it, but don't. You can de-emphasize sort of the nuts and bolts of this sort of more than you would. Okay. Yeah.
I do have a few like logistical questions about the midterm in terms of like, do we need to bring a V table and like a T table?
I'll bring everything that you need. The only thing that you will need is a writing utensil and a calculator. It's
Okay.
not your phone.
Okay. And then is there any way that you would be, do you have like the equation list that you'll give us that like with all the equations on
Don't worry about the equations. The equations will not. If you're worried about the equations, you're worried about the wrong thing. Okay, spend your time and effort to looking at it. So it's just going to be a sheet of formulas that have different stuff. Yeah.
Can we read that in advance?
So that's what we just don't worry about that. I'm not going to give you that because you don't worry about that. Okay, so worry about conceptual stuff, understanding so what's happening with this stuff. Okay. Other thing too, folks, we got 2 more lecture decks. And that's it. Like we got ANOVAs and we got factorial ANOVA. I mean, we've got a good chunk of the class. So now ANOVA stuff gets a little bit like there's more stuff going on. There's more sort of moving parts and things like that. But we're in a really good spot. Okay. We've covered a lot of information. Make sure that you're going back to the very beginning and sort of making sure that you've got a handle on concepts and things like that going on in lectures. Make sure you got a handle on your readings. If you have questions, so let me know. But I think you're in a good spot. Okay. So nice work. Nice work. Everybody is impressive. We're all winners.
Did you see Haley shine or just our perspective?